As I'd like to mention at the beginning of some of these videos, a lot of this is stuff that you should be able to figure out on your own just with exploration. So I would encourage you to try these notes without just watching the videos, but just seeing how far you can get and then using the videos as a way to check your work. Especially with this warm-up here, this is simply a review of what we just got finished talking about with parametric equations. We've got a pair of parametric equations right here, and we're asked to eliminate the parameter. Same thing over here. So I'll just go through that real quick. We'll solve for t in the easier one, and we'll replace t with the thing that t equals in the more complicated one. So in this case, we have t equals x over 2, so I'm going to replace the t with x over 2 here, and I'm going to replace the t with x over 2 here, and that's going to end up giving us 1/8 x cubed minus 1/2 x squared. Trying the same thing over here, basically the same process, right? We have x over 4 this time equals t. So when I replace t with x over 4, we've got 8 divided by 64, which is 1 over 8. And we've got 8 divided by 16, which is 1 over 2. All right, so that was just a quick little warm-up, reminding us that we know how to eliminate the parameters. All right, the new stuff is actually just a new way of writing old stuff. So this new notation is called vector-valued functions. And basically what it is taking a pair of parametric equations and writing it as a single vector. If you forget, vectors are a quantity that has both magnitude and direction. And we can find its magnitude, we can find its direction using various equations. But if we're just interested in the components, then we can write the x component in the first half of the ordered pair and the y component in the second half of the ordered pair. Now, if we're calling our vectored valued function p of t, then probably that p stands for position. So it's a location function, and we're actually locating where a point is at a given time. This is very similar to what we've seen with motion along a straight line, but now we have motion in a plane, so we can go up and down and left and right. We can go all over the place. We can go curvy stuff. Now, we're not going to deal with 3D, but we could extend this to 3D by having a third dimension controlled by t as well. Probably we would call it z of t. But we're not going to go there. We can just basically figure out how it works on 2D and imagine that we can extend this onto more and more dimensions. All right, so this is the position on the x, on the horizontal directions, and this is the position for the y or vertical directions. So we can have an x and a y both depending on t. All right, cool. So looking at the two vector value functions that we saw in the warm-up, we can just write them instead of as two separate equations. We can write them as an ordered pair with these angled brackets. And the question here is to compare them. What is the same? What is different? And it's pretty obvious, I think, that what is the same is that when you eliminate the parameter, you get the same equation, y equals 1/8 x cubed minus 1/2 x squared. In other words, the path is the same. The path that these two particles are traveling, is the same. So what is different? Well, as we've talked about before on other examples, we've talked about how the time is different. For example, we might not, while it's clear that we're going to hit, I don't know, the point 1, -3/8 at some point in time here, right? When x equals 1, y is going to equal -3/8. We're going to hit this point at some point. We're also going to hit that same point at some point over here, at some point in time. But we're not necessarily going to hit it at the same point in time, right? So these guys are not traveling in tandem, right? They're following the same path, but not necessarily starting at the same time or perhaps not necessarily traveling at the same speed, and you can imagine, based on comparing these guys, you can imagine what the difference might be, but we don't have to imagine it. We've got a link that I built in advance. Both of these work. I like this one better because it's set up so that there's not as much waiting. So if you want to follow that link, or you can type it in if you feel like it, or you can just watch what happens when you hit play. But before I hit play, let me show you how I made this. So the two curves are given here in terms of t. Desmos knows that t is your parameter. And then I created some points using the slider A. Notice I used the same slider for both of these guys. And then I'm just going to let my slider A travel from small values to big values, and we'll see the two paths get created. Actually, we'll see the same path get created twice, once in red and once in blue. Notice that the red is the first one that we graphed. That was eliminated. That's the one where x equals 2t. When we see the one in blue, that's the one in 4t. So we'll go ahead and push play and see what happens. Where's the blue? Oh, there it is. It came from behind and it's going faster, right? So it looks like they're traveling the same path, but blue is traveling that path twice as fast. And that should be fairly evident based on the equations involved. All right, so that's a nice visualization so we can see that they're, the two different pairs of parametric equations, the two different vector value functions, create the same path, but they don't create it the same way.